the hurdles will be more. Each time we are washed away, we bounce back to the shore. We know we lead the way, keeping odds at bay. See the sunrise tomorrow, inspire the world to follow.
Okay, so in the course of electrical machine 2, today we are going to start our lecture number 12 on module number 2, single phase induction motor. In our last lecture classes, we are developing the cross field theory so that we can show that how the interaction of different fluxes or different EMF which is responsible for the production of these fluxes produce torque in single phase induction motor. And in that context, we have discussed two EMF. One is transformer EMF ET, another one is speed EMF or rotational EMF ES or ER. And today we will show you how a cross field is produced inside the rotor. That physics we are going to discuss today. Okay. So this is my objective, develop the concept of cross field theory. So now if we look into this figure, so this figure is basically the distribution of motor winding in the stator slots of a two-pole machine. This figure shows that the distribution of stator winding. This figure shows the distribution of stator winding, distribution of motor winding in stator slots for a two-pole machine, right? So now what happened, we give single phase supply to the stator of a single phase induction motor, pulsating supply or alternating supply. And for giving this single phase supply in the stator winding, which results in production of the two flux, one is mutual flux, and another one is stator leakage flux, flux. So these two flux produce when we give a pulsating supply to the stator winding. Now this mutual flux cross the air gap and links both the rotor bars as well as stator turns, both rotor bars and stator turns. Now as it is linking both the rotor bars and stator turns, so Faraday's laws of electromagnetic induction comes into picture. So basically a transformer action will occur. So basically a transformer action will come into the picture. Now due to this electromagnetic induction or transformer action results in production of stator counter EMF, which will produce stator counter EMF, which we can denote it as EB, or best it is denoted as ES, and rotor EMF we can denote it as ER. So there is production of these two EMF. One is inside a stator, that is the counter EMF, and one is inside the rotor, that is ER. Now if the stator number of turns equals to rotor number of turns, that is if NR by NS equals to 1. So if these two turns are equal, then we can say that ES is equals to ER. We can say the magnitude of both the stator counter EMF or rotor EMF, induced EMF, both are same. So now we can establish the logic. So we can express the rotor quantities in terms of stator quantities. Okay. So now this two, we have seen that there is a two magnetic field is produced. One is mutual flux and one is stator leakage flux, and stator leakage flux is only links the stator number of turns. It is only link the stator turns, so which has an effect of leakage reactance drop in the stator winding. So it has an effect of leakage reactance drop in stator winding. So whatever may be the flux, whether it is the mutual flux or the stator leakage flux, both produced from the magnetizing component of stator exciting current I phi. So this exciting current of stator is responsible for the production of both the fluxes inside this single phase induction motor. Okay. Now mutual flux is in the nature of pulsating in nature. So mutual flux is basically pulsating is nature. So it basically if we recall the figure, it basically pulsate along the this axis, vertical axis or y axis. So that's why it is known as, this is known as y axis or main field, FIELD means main field axis of phi m. Right. Now we have seen that there are different starting methods we applied to make the single phase induction motor self-starting, and we have discussed so many methods like capacitor start, capacitor run, split phase, resistance split phase, reluctance, repulsion start motor, all these things. Now suppose the rotor now start rotating in omega rad per second. So now the rotor start rotating. So what will happen? The rotor bars cuts this main flux. So this main flux will cut by the, so if we, so this is the main flux, so this is my direction of main flux along the y-axis. So this is my direction of main flux along the y-axis. So what will happen as the rotor start moving, so this rotor bar will cut the magnetic flux and generate voltage due to speed EMF. So due to speed EMF it will generate voltage. So it will cut the flux, rotor bar cut flux phi m results in induced EMF due to speed action. Now we know the rotor are symmetrically closed. Squirrel cage rotors of single phase induction motor are symmetrically closed with end bars. So it is symmetrically closed with end bars. So as the rotor are symmetrically closed circuit with the ends bar, so due to this induced EMF, a current will start flowing through the rotor. So a current will start flowing through the rotor winding. So there is rotor number of turns NR, and suppose current is R, IR, so it will produce a ampere turns. Now if we divided this ampere turns with the reluctance of the material of the rotor, it will produce the flux inside the rotor, which is denoted as mainly, I have mentioned a phi r, but it is mainly denoted as phi c. So now a flux is producing inside the rotor phi c. So basically this phi c acts in space quadrature in 90 degree to the main flux. So the term or the theory called cross flux theory or cross field theory. So this is my phi c. So this is my phi c. So it is in space quadrature with the main field flux, and this phi c remain in space quadrature with respect to phi m, and we will establish rigorous proof or rigorous evidence in later on, and previously we have proved it that it remains in space quadrature. Okay, so now one thing you should keep in mind, so whatever flux cross flux is producing because of the current, because of the speed EMF, because of the production of speed EMF, so because the rotor is not in standstill condition, so when the rotor is standstill condition, this will disappear. So this will disappear in standstill condition. So this will disappear in standstill condition. Now we will see some complex notation used in this theory. Complex notation to identify various component of voltage, current and flux. So for that, first we should keep in mind that subscript T and S. T for transformer EMF, S stands for speed EMF. Okay, now second we should remember M and C. EMF produced in the main winding or cross winding or cross axis or main axis. So M stands for main axis and C stands for cross axis flux, cross axis of the flux. Okay. And third we should remember EMF producing current effect on main and cross axis, that is y axis, which is known as main axis, and x axis, that is the cross axis. So these three we have to remember: T, S, M, C, Y, X. Now if we say ETHY, now if we say ETMY, so what it represents? ETMY. So what is represent an EMF induced in the rotor due to main winding flux. So this is EMF in main winding due to transformer action. Okay. So this is due to transformer action, main winding flux, which resulted current and EMF in the y-axis. So due to transformer action, whatever EMF produced, or whatever current, whatever EMF, MMF will produce, whatever flux will produce, that will react in the y-axis or main axis. Okay. Now what is stands for ESMX? ESMX. Now due to speed action, main field flux and final current. So this is the EMF produced due to the speed action. So this is due to speed action on the main field flux, and whatever the final current, whatever the EMF will produce, whatever the flux will produce, that will act on the x axis, that is the cross flux axis. So this is SMX. Now there are two other terms which is we should know. One is ETCX. So this is induced voltage due to transformer action in the rotor bars in the cross field axis. TCX. So EMF due to transformer action which produce current, which is responsible production of the flux in the cross field axis C or X axis. And another one is ESCY. Now that is speed voltage produced by the cross field flux in the y axis. So this is speed voltage due to cross field axis in the y axis. This is EMF in the due to speed action due to main axis flux in the cross field axis. This is in the main field axis, and this is TMY due to transformer action production EMF which produce in the main axis, which is induced in the flux in the y axis, and this is due to transformer action a EMF will produce which will produce a current in the cross axis or x axis of flux. So these are the few things. So proper grouping of this voltage along with its impedance drop enables. So proper grouping required of these 4 ETMY, ETCX, ESMX, ESCY. So proper grouping, and along with their impedance drop, of rotor winding, which enables us to determine the rotor current. So we can determine the rotor current from these concepts. The current component are identified the rotor axis along which they produce MMF. The current component are identified by the rotor axis along which they produce MMF. Now one thing we should remember, that this component of current and voltage, of course no separate existence, or they have no separate existence. They are only chosen for the purpose of analysis. They only chosen for the purpose of analysis. Only. So build the concept. The task is to locate each them in space and time, so that we can put them in space in time, that is in phasor. We can place that 4 quantity E, T, C, X, E, S, C, Y and so on in this space and time according to the phasor diagram, so that we can develop their quantitative expression, so that we can develop the expression of all the force, and we can prove that how the torque is produced, So this is my things. So this main things is to build the phasor diagram, and this from the expression phasor diagram we can derive the expression of these 4 quantities, and we will derive the torque and power equation to analyze the operating function, different operating function or equivalent circuit or description of phasor diagram through cross field theory of single phase induction motor. So this is all about my today's class. Okay, so this is all about my today's class. Thank you.